Okay, this is my third video for my Algebra 3 Prerequisite chapter number 3, in which we're really quickly going to talk about nth roots, or perfect nth roots. Up until now, we've been discussing roots that are particularly square roots. When we define the principal nth root of a number a, we write this as the nth root of a using this little n right here on the outside. The thing is, when you write the square root of a number, say the square root of 4, another way to write this actually would be 4 with a little 2 out here, where we're saying we're taking the second root of 4. And the definition of this really is this here. We say that if n, the index, and we want to make sure we make a note here, is on the outside of this, if the nth root of a is equal to b, what we're really saying is b to that power of n is equal to a, okay? So we can have cube roots, fourth roots, fifth roots, any root you want, but we're saying what number could I take times itself, the index number of times, to get a exactly, and that number is going to be b, and just by definition we say b to that number, times itself that many times is equal to a, okay? That's the definition of it. So one note I do want to point out here is this: if n is odd, okay, if we have an odd index, if I took the nth root of a to the n, I would just get a, okay? But if n is even, if I take nth root of a to the n here, I would get the absolute value of a. So the point here is it's always got to be a positive output if you're taking an even root, whereas if you have an odd root, it's possible it could be positive or negative. It's any real number here. So taking a look at these examples down here, just really quickly, we say that, the cube root of -8, we're really asking what number could I take times itself 3 times to get -8, and to my mind here, we say, it comes to me that -2 to the third power would be this. So by the definition of nth roots here, we say, well, the cube root of something cubed would just be that number here. We'd say it'd be -2, okay? And it can be negative because I can take a negative times itself an odd number of times and get a negative output here. So the fifth root of 32, what could we take times itself 5 times and get 32, okay? And so thinking about this, we say, well, 3 times itself 5 times. 3 times 3 is 9, times 3 is 27. That's going to be too big. How about 2? So we'd say, well, maybe 2 to the 5th. And it is, as a matter of fact, 2 to the 5th. That does come out to be 32 exactly. So that's a perfect nth root, or a perfect fifth root. So we'd say 2. In this case, a positive 2. Okay, so looking at this last example, we say, well, what's the square root of 16? Or sorry, not the square root of 16, the fourth root of 16. What could we take times itself 4 times and get 16? And again, this one has to come out to be positive because we're taking a fourth root. I couldn't take something times itself 4 times and get a -16. It's got to be a positive 16 here, okay? So I was able to get these very, very quickly. If you look at this chart right here, it is worth your time to note some very particular perfect, cube roots, perfect fifth roots, fourth roots, okay? But these are notable, okay? As a matter of fact, like say the cube root of 1,000 would be 10. 10 times itself 3 times would give us 1,000. So take a moment to really look over these and say, well, when I see these numbers, I'm going to identify them as being perfect, say, thirds or fourths or fifth powers of something, okay? What I really want to do is basically tie these nth roots into our product and quotient rules again. So from previous video, you know that the product rule, it says if you take the root of a times b, that's really the root of a times the root of b. Well, in this case, we're going to expand that definition to say, well, the nth root of a times b is the nth root of a times the nth root of b. And likewise, if you had the nth root of a times the nth root of b, and they have to have the same indices, the index has to be the same on them, okay? Then we can join them together and put them under one nth root radical, and we say it's the product of those two things on the inside there. And likewise with our quotient rule here, we say that the nth root of a quotient here is the nth root of the top over the nth root of the bottom, where b can't be 0. Or if we had the nth root of a over the nth root of b, where they have the same indices here, we could join them together and say it's the nth root of all of those, a over b, okay? So let's go ahead and use our product and quotient rules to simplify some nth roots, not just square roots, but nth roots, okay? So we say the cube root of 40. What we're really looking for is a perfect cube, or a number that can take times itself 3 times and get a cube here that goes into 40 evenly. So this is why we really want to know these values right here. So like 1, 8, 27, 64, 125, 216, 1,000. But I recognize that 8 is a factor of 40 here. So we could rewrite this as the cube root of 8 times 5, which using our product rule here is the same thing as the cube root of 8 times the cube root of 5. And the cube root of 8 we know is 2. So we really get 2 times the cube root of 5. Okay, so let's try this again here. The fifth root of 8 times the fifth root of 8. Now what I know is this: essentially, 8's not a perfect fifth. But I do know that using our product rule, we could rewrite this as the fifth root of 8 times 8, which is really the fifth root of 64. The fifth root of 64. Now 64 is also not a perfect fifth here. You notice that I don't have that on the list here. But we could say that 64 is 4 times 16. That doesn't work, I guess. We could also say that 32, that's the number we're going for here. 32 goes into this evenly. So we say the fifth root of 32 times 2, where 32 is a perfect fifth. We can now extract a 2 out of this, and we say 2 times the fifth root of 2 left over, and this would be our simplified form. And really quickly, we'll do one with the quotient rule here, but I can't simplify 125 over 27 here. But I do know that if I were to take the cube root of a quotient, it's the cube root of everything on top over the cube root of everything on bottom. And the nice thing about that is I recognize that 125 and 27 are perfect cubes. 125 is a perfect cube of 5, and 27 is a perfect cube of 3. So really simplifying this, we come out to be just 5/3. Okay. So this last example here, what I want to look at is really just combining like radicals. And remember, like radicals mean you have the same radical factors. And in this case, the cube root of 3 and the cube root of 81, those aren't the same. But I do know this, 81 here, we could say, are there any perfect cube factors that, say go into 81 evenly? And as a matter of fact, 27 goes into that 3 times. So this could really be rewritten as 3 times the cube root of 27 times 3 minus 4 times the cube root of 3. And the cube root of 27 is going to be 3. So we'll take that out front and we'll multiply it by whatever was already out there. In this case, we have a 3. We say this is 9 now times the cube root of that 3 that was left over, minus 4 times the cube root of 3. And I notice now that we have like radicals. These are the same radical factors. So 9 cube roots of 3 minus 4 cube roots of 3, using our distributive property there, would be 5 cube roots of 3. Okay, and that'd be our simplified form.